Folks, in this class we will talk about decision making under uncertainty precisely, but nonetheless, if you look back, as a manager you have to make decisions all the time. Okay, so what differs is the amount of information that you have and the context of the information. Okay, that's what it differs. In other words, if you look at the context, some of the information that you have is known for sure. That is the decision making under certainty. Okay, in some cases the context is you have some information available, but you are not sure about the reliability of that information. So that is the decision making under uncertainty. For example, right now the economy is bad, right? Now the economy can improve or the economy can go worse. So you know that it's one of the two cases. Either the economy is going to improve or perhaps stay the same or go down. Okay, but you do not exactly know tomorrow how the economy is going to be. So that is the uncertainty. The certainty would be, okay, the economy is going to be better tomorrow. That is a certainty, but we don't have that information. Okay, we don't have that information. So this is the context. Based on the context in which we have to make a decision and the source of the information, now we can broadly classify decisions as decision making under certainty as well as decision making under uncertainty. So for the problems that we have dealt with, you can say that those are the decision making under certainty. Okay, so that means the state of nature is only one state. That is, we know that things are not going to change. Okay, that's what it is. So some of the things that LP and project management, in some cases of project management, that when we get to that you would see, those are the instances in which the decision making are under certainty, like a product mix problem. So we know that out of these 5 different products that we make, okay, what is the level of activity of those products that we want to make? Okay, we know that we are going to make out of these 5 products, but we are trying to determine which ones to make at the level of activity. The diet problem, if you look at it, like how much of those, the basic ingredients to use to arrive at a meal plan that would have the necessary vitamins and other things the body needs, and keeping the cost low, distribution, scheduling. These are the problems of decision making under certainty. In your day-to-day life, let's say that if you got $1,000 and then you want to decide about you want to put it in a CD, that is again decision making under certainty, because you know the information that several banks offer their CDs for 1 year at. So based on that, you choose the bank that offers the highest rate of return for the CD, and they have to go with that. If they say 5.5%, it's going to be 5.5%. Now let's look at some of the examples of decision making under uncertainty. In this case, the outcomes could be 1. Okay, the total uncertainty could be, okay, like for example, tomorrow the economy is going to be good, or the stock market is going to be, or the Dow Jones is going to be better than today, equal to today, or worse than today. So it can be one of the 3, but we have no idea about what it is going to be tomorrow. That's a total uncertainty. Okay. On the other hand, there is a 20% chance that the Dow Jones index could be better tomorrow. There is a 50% chance it's going to be very similar to what it is today, and there is a 30% chance it's going to be less than today. Okay, now here we know that one of these 3 states would exist tomorrow, but we are putting some probability or some estimate. So that is a decision making under risk. Okay, so when we don't have this probabilistic estimate, this is total uncertainty. Okay, now some of the examples could be drilling for oil. We don't know whether we are going to strike the oil or not. Okay, developing a new product. We don't know whether this product is going to be successful or not. Okay, and some of the uncertainty that comes into play is the R&D cost, the demand, and so the competition may come out with a product. It could be a substitute product, maybe better than this. We have no idea about that. Okay, and there are many more examples, and some of them are listed here on the screen that you can see. Now let's take it for example. Let's just go through this and what sort of tools and techniques are available to us. Okay, in this kind of situations. That is decision making under uncertainty. Let's consider a problem, oil drilling problem. Okay, now the state of nature could be wet or dry, meaning that you are going to strike the oil or the strike or the oil is not there. If you drill a hole and then if you strike the oil, then if oil is found, then it is $800,000 minus $200,000 for the drilling. $600,000 is your net profit. Okay, if you drill and if there is no oil, then you lose $200,000. That is your drilling cost. If you do not drill, there is no loss, there is no gain. Okay, so this is the most simplistic situation. What is the best to do? Now, in a case where this is a decision making under total uncertainty, we don't know what's the probability that that we're going to strike the oil or we don't going to strike the oil. Okay, in that absence, total uncertainty, what is a decision? There are about 4 different tools that one can use. One is an optimist. A person is totally optimistic, meaning that whatever the person does, the best happens to the person. That's a total optimistic, which is also called maxi-max criteria. Okay. In the other case, the person is totally opposite, totally pessimistic. So here, the person assumes that whatever the action he or she does, the state of nature is always its enemy and gives the worst blow possible. That's a total pessimistic. Okay. The second guesser is, like for example, what is the probability, which state of probability is most likely to happen? Okay, because that's what most likely to happen. Then let me go choose the criteria which is best under that. See, Joe average is nothing but taking the average payoffs of each one of these alternatives that we have on, and that's the Joe average. Okay. Now, let us go with the base decision rule. Okay, which is nothing but here we have some information about the prior probability. Okay, suppose that the oil company estimates that the probability that the site is wet, that is there is an oil, is 40%. Then naturally that it is not there is 60%, because either it has to be wet or it has to be dry, one of the two. So the total probability is nothing but wet plus dry, which should always sum up equal to 1. Okay. Now what do we do in this case? If that is the case, the base criteria says take the expected value. There is a 40% chance that we make $600,000. There is a 60% chance we lose $200,000. So that's what you see here. Okay, take that weighted average of those payoffs with respect to the probabilities. So that's about $120,000. So there is average expected payoff is $120,000. So what it basically says is, suppose if you were to carry this experiment out, let's say 100 times, in about 40% of the cases you would have had oil. In that case you would have made $600,000. In about 60% of the cases, you would come out empty. In that case you would have lost $200,000. So the long run average, that's the long run average, is about $120,000 in profit. So the expected value of not drilling at all is nothing but 0.4 times 6. Otherwise, that is 0.4 times 0 plus 0.6 times 0, which is nothing but that. So now between the two, we go with the highest expected value because it's a profit maximization. If it is cost or time, then we go for the lowest number because that is what is better for you. Since it is profit, we are choosing a number that's a larger number, which is $120,000. So according to the base decision rule, choose the criteria that maximizes the expected payoff or expected benefit. In this case, since it is profit, we go for the highest number. If it was cost, then we would have gone for the lowest number. Okay. Okay, now some of the things that you got to appreciate about the base decision rule is, now not only we know about the outcomes, the payoffs, and also the probabilities. Okay, and we are basically looking at a situation in an expected sense. That means long run average. Okay, so that is the thing that we'll look at. Okay, and we can handle complicated situations involving multiple related risks in several of these cases. Now here is a schematic representation of the same situation, okay, which is called a decision tree. This is a very simple problem, so the power of decision trees are not obvious over here, but if it is a sequential decision making process, you would see the power of decision tree. Okay, and here the decision tree has two different kind of nodes. One is a square node called a decision node. The other one is a circular node called a chance of nature or state of nature node. Okay, so whatever line that comes out of a square is our alternative or decision. So it is our decision whether to drill or not to drill. We can choose either one of these two. Okay, so that is what you see here. Okay, now when you come to the state of nature, here we don't have any control over what is the outcome. We do not control whether the oil field is going to be wet or it is dry. We have no control over that. That's why we call it state of nature. So the number of lines that comes out of a circular node denotes the number of states of nature that you have in your problem. Okay, any state of nature node always have a probability associated with it, like the wetness is 0.4, the dryness is 0.6. At the end of the tree is the payoff that is listed. So the construction of the decision tree starts from left and proceed towards right. When we begin to solve the problem, we proceed from right to the left. So what we do is we go to the farthest right and take the products of the probabilities and associated payoff, okay, for the states of nature, then sum them up and list it by the side of the node. Okay, so we do that for each one of the nodes that's the farthest right. Then we continue the procedure until we go towards the left, until we reach the final initial point of decision, and that's when we would have solved the problem. So in sequential decisions, the power of decision tree becomes extremely valuable, because now until then, if it is a simple decision tree just like what we saw, we could just the way that you saw there, we can take the sum product of the probabilities and the associated payoff and make a decision. But if you have got several steps, then we have to build that thread between different payoff tables, which is going to be very confusing. Suppose if it is confusing for us when we are doing the problem, just imagine how difficult it would be for you if you would explain the same procedure to your higher ups. They would not be able to see. That's where the power of decision tree comes extremely valuable in sequential decision making. Okay. Now, the prior probability is based on the information that we have in historic information that we can use. Again, the thinking there is the past is a good reflection or a mirror for the future. But things can change. Okay, so here incorporating new information. Okay, sometimes we can undertake market surveys or test marketing or seismic testing, etc. For in case of oil, we can do a market survey of a focus group to see whether this group is going to be more favorable to the new product or not favorable to the new product. We can do those in many different ways, either by asking people focus group, we can test market the product. I mean, like for example, there in Costco or Sam's Club or any of these places, you can have your product out there, you can just put it out on the tray and just see what is the traffic, and so how much of the traffic stops by to taste the product, and then how much of that traffic that tastes your product does end up buying that product. Okay, so that could be test marketing. So those are valuable sources of information to go and then bring them into the decision making, in terms of the probabilities, and make a good informed decision based on that. Okay, now let us look at what is the value of this sort of information. Okay, the value of the information. Okay, whether should we basically go with what is given to us, or should we investigate and do a further research, to find the newer probabilities to go and then refine and revise our decision making situation. Okay, now we basically did discuss this slide earlier. Okay, so here is based on this, what is the expected payoff? Some product of the probabilities and the associated payoff gives us $120,000 for the drilling, and not drilling is 0. So that means our decision based on this information what we have is to go for the drilling option. Okay. Now, suppose if you can get more accurate information on this probabilities, or what state of nature is going to occur with surety. Okay, what is, if someone is there to tell you that, look, I can tell you exactly what's going to happen, whether it's going to be wet or dry, I can tell you with 100% certainty, and if this person is going to cost you money, okay, how much should you be willing to pay? That's the perfect information. Wet or dry, one of the two, that's the perfect information. Okay, so what is the maximum that you are willing to pay for that sort of an information? So that's the expected value of perfect information. What that is like this person says, yes, it's going to be wet, that we know that we have to drill and we make $600,000 in profit. So what is that probability of making that? That's 0.4 times 600. That's that expected payoff with perfect information is 0.4 times 600. Okay, plus this person says, no, it is going to be dry and nothing else, then that is losing $200,000. If we drill, or if you don't drill, because this is the best option for us, not to drill and do not incur any cost at all. That is 0.6 times 0, which is nothing but 0. So this is the expected value of perfect information. In other words, the state of nature is revealed to you, and that is what is going to happen. Then accordingly you can select your choice. Suppose if the state of nature is wet, then your decision is to drill. If the state of nature is dry, then your decision is not to drill. So this is that expected value with perfect information is $240,000. Then what is the value of the perfect information then? So without that information, without this perfect information, we went with the expected payoff of making $120,000. But if we have this information, perfect information available each time, accordingly we can select our choices each time, then we can make the max, which is 240. So the difference between the expected value with perfect information and expected value without any information, that is an outside help, okay, that's 120. The difference is $120,000. So at most you can pay $120,000 to obtain this perfect information. Of course, in reality, what we know is we would never know beforehand exactly what is going to happen. Okay, so we can conduct the market survey, we can test pilot the product to see the likeness or likelihood or unlikelihood or success or failure of those ventures. Okay, in other words, we can poll a small population. Okay, during the times of elections, basically you do see that which candidate is favored and which is not, the likelihood of winning on that particular day with a margin of 4% or 3%. What is the basis? The basis is they did not ask the entire US population to see who they are going to vote. So they have a focus group, or they have a sample size. Based on that sample size, they predict who the the likelihood of who is going to be the next president. Okay, so that is what they do, is they do that sample. Okay, now here in this case we can basically do a seismic survey to find out the probability of striking the ground being wet, or the oil fields being wet or dry, with a little bit more accuracy than historical information. But that's going to cost us money. But nonetheless, any seismic survey that we do did not exactly come out with a perfect information, but a good information is what it comes up with. Okay, so the best that sort of information can get us is an improvement of $120,000 over what we could do without that information. Okay, if it can get us all 120, so that means the efficiency is 100%. If it can get us, let's say, about 80 out of this 120, so that means we got 80% 80 out of 120 would be the efficiency. That is nothing but 2 over 3, about 67%. Okay, so that's how we gauge one firm being more efficient than the other firm in terms of getting the sample information. Okay, so in that case, because the survey result is going to get us an information that is not perfect, so that's why we call it imperfect information. Okay. Okay, suppose a seismic test is available that would better but not perfectly indicate whether or not the site was wet or dry. So a good result usually means the site is wet, but not always. Okay, bad result usually means the site is dry, but not always. There is a likelihood. Okay, let's say that you do go back to about 100 past seismic test sites. Okay, seismic result, that is a good and actual state of nature. Okay, about 30 times, when the when the ground was wet, we get the good seismic result. About 20 times, actually it was dry, but since we tested at a site, we got the false result as being good. Okay, maybe it was good, but the oil was not there. So we got total out of 100 times, about 50 times, we got the good result. Out of those 50 times, 30% was due to the wetness, or 60% of the times. Okay. Then we had the bad result. Although the actual site there was oil, but the place where we conducted it was dry area, we falsely concluded then it's a bad site. Okay, or bad result. Okay, and about 40% of the times, or 40 out of 50 times, when actually it was dry, we did get the result as a bad. Okay, so that means here you see that 80% and 20%. Okay, so together we got out of 100, total wet sites were 40, total dry sites were 60. Now, this is a decision tree for the problem that we were looking at. Okay, so here we are just looking at the probability, not the entire decision tree. Okay, so now here, a probability of a good test, probability of a bad test. Okay, that is bad results and good results coming out. Okay, now our decision whether to drill or not to drill. Okay, in other words, suppose if the seismic results, the agency that you hire comes back and says, hey, look, so we got the good results on this field. Now the decision is back in your lap whether to drill or not to drill. If you drill, then what we want is probability of the fields being wet when actually the results that you got from the field test were good. What is that probability? That's what we want. Okay, then there is also a likelihood of a false reading. What is the probability of finding a dry ground given that the results were good? Okay, we need that one here. Probability of not drilling at all is no payoff there. But nonetheless, if it's going to cost you money to do the test, then likewise those monies have to be subtracted from here. On the other hand, if the test result is bad, but again the decision is back in your lap whether to drill or not to drill, in that case we need to get these figures. So here these numbers would be different than these numbers here. So if the bad result, then the probability of dry being that, remember we said 80% and 20%, that's what it is going to be. Here it is 60% and 40%. Okay, so those are the things that we found. Okay, now if you do that, 60%, 40%, 600 times 0.6, then 0.4 times minus 200. Okay, so that is a $280,000. $280,000. And not drill is that 0.6 times 6 is 36, 36 and minus 80. Yeah, that is 280,000. Now here, if the results were bad, then that payoff is going to be $40,000 loss. Okay, and what is the expected value here? That is 0.5 times 280 plus 0.5 times. What is the best decision here? So by drilling, we lose $40,000. By not drilling, our payoff is 0. So you basically take that payoff, 0.5 times 0. That is 0.5 times 240 is 280 is 140. That's what you see here, 140. Okay. And over here, the same thing, 0.4 times 600 plus 0.6 times minus 200. That is that expected payoff there. By not drilling, it is 0. 120 is more than 0. So you go with 120. So here, do seismic test or forego the test. If you do the seismic test, you hope to make $140,000. But if you forego that test, it is $120,000. So that's based on our analysis. Earlier analysis also was about the same. So the expected value of sample information is 140 minus 120, which is $20,000. So I'm going to leave these things there. So I suggest to you to go back. This is a similar discussion that what we did on the posterior probabilities. What actually we measure in the field is not exactly what we can directly go and then use. We had to go through this recalculation of the probabilities. Okay. Say for example, you may get the survey results as being positive. But what we want is we are going to have a success given that the survey results were positive. That's what we want. Okay, so what we measure in the field is nothing but given that you ask the favorable people, who is going to be the next president. Okay, so they might tell you that. What we want is the reverse side of that information. And the next few slides are going to cover exactly how to get those things.